In this video, we will look at the extraction of iron from its ore in the blast furnace. We'll look at the chemicals used in a blast furnace and the temperatures involved. Iron is an abundant metal which is relatively cheap to produce. Ores containing a high proportion of iron can be found throughout the world. There are many compounds of iron that can be found in nature. But the one that's most common for extracting iron, and the one that will feature in this video, is hematite. Hematite is a naturally occurring form of iron 3 oxide, Fe2O3, and it's about 70% iron by mass. What this means is that with perfect extraction, putting 1 kilogram of ore in, we should get 0.7 kilograms or 700 grams of pure iron out. However, it's not quite that simple, so let's look at the details. Iron can be extracted from its ore using carbon, which is great. Carbon is very cheap and very available. The carbon used to extract iron is commonly obtained from coal. Coal often contains hydrocarbons and other volatile impurities. Heating coal to over 1000 degrees Celsius will drive off some of these impurities, forming something we call coke. Coke is a much purer form of carbon than coal, meaning it introduces fewer impurities into our iron. When hematite is reacted directly with carbon, a redox reaction can occur. Hematite, Fe2O3, is reduced to iron. And at the same time, carbon is oxidized to a mixture of carbon monoxide and carbon dioxide. The exact stoichiometry will depend on the conditions. If we look at the reactivity series, we're reminded that carbon is more reactive than iron. So when we heat iron oxides with carbon, the oxygen passes from the iron to the carbon. So far this seems pretty simple. All we need to do is heat hematite with coke and we'll get our iron. If only it were that simple. Pure hematite melts at 1565 degrees Celsius, while iron melts at a very similar 1538 degrees Celsius. Carbon, however, is relatively stubborn. It won't melt, instead it sublimes at a massive 4827 degrees Celsius. This means, at least until we reach about 1500 degrees Celsius, we'll be dealing with reactants that are all solids. Solids are difficult to mix and the reaction will be extremely slow. Now, even if we did heat enough to melt the hematite, that's not necessarily a massive improvement. Mixing in the much less dense carbon would still be quite an intensive process. Fortunately, we don't need to get to nearly 5000 degrees Celsius for this reaction to work quickly. Instead, we can take advantage of a nifty feature of carbon. When carbon reacts with a limited supply of oxygen, it forms carbon monoxide in an exothermic reaction. With further oxygen, carbon monoxide can react to form carbon dioxide, again in an exothermic process. If, under the same conditions, we use carbon monoxide instead of carbon as our reducing agent, we'll have a much more effective reaction because it will be much easier for a gas to be mixed in. In the blast furnace, where this reaction happens, the hematite may actually still be solid, but the iron we get out at the end will definitely be a liquid. The most important reaction to remember here is the reaction between hematite and carbon monoxide. The reaction between hematite and carbon does occur, but much less so. Next, we're going to look at one of the most important features of real-world chemistry, the impurities. Real coke and real iron ore contain impurities. The problematic impurity we'll be looking at is sand, which is mostly silicon dioxide. You may hear silicon dioxide called silica. If we don't remove most of this impurity, it will end up in the iron, giving it properties that we don't want. To remove silicon dioxide, we're going to introduce a chemical to react with it. The chemical we'll be adding is calcium carbonate in the form of limestone. Calcium carbonate doesn't actually do the job itself, but at high temperatures it can thermally decompose, producing calcium oxide and carbon dioxide. calcium oxide can react with silicon dioxide impurities, producing calcium silicate, CaSiO3. This form of calcium silicate has a melting point of around 1540 degrees Celsius, very close to that of iron. Molten calcium silicate will naturally separate from molten iron because it's about half as dense. Introducing calcium carbonate allows us to produce a layer of impurity that we can separate purely by opening a tap. We call this layer slag. Next, we need to go to the very core of how iron is extracted, the blast furnace. In the whole of 2019, 2.5 billion metric tons of iron ore was mined worldwide. That's the equivalent of 7,500 times the mass of the Empire State Building. We need massive pieces of equipment to process all that ore. This is where the blast furnace comes in. A modern blast furnace is about 15 meters wide and about 35 meters tall. It has the volume of about 2 Olympic swimming pools. From one of these furnaces, you'd expect to get about 10,000 tons of molten iron a day. The full design of a blast furnace is very complex, so we're only going to look at a simplified version. In the first step, coke, ore and limestone are added to the furnace from the top. The coke provides the carbon, the ore provides the iron 3 oxide, and the limestone provides the calcium carbonate. In the next step, hot air between 900 and 1300 degrees Celsius is injected into the bottom of the furnace. It's these blasts of hot air that give the blast furnace its name. Oxygen from the air quickly reacts with the solid carbon in the coke, producing carbon dioxide gas, which rises up the furnace. This and other exothermic reactions raise the temperature at the bottom of the furnace to between 1500 and 2000 degrees Celsius. As carbon dioxide rises and mixes with more carbon, it reacts to produce carbon monoxide. This is also an exothermic reaction. The carbon monoxide rises up the blast furnace to do the most important job, reducing our iron oxide. The carbon monoxide reacts with the iron ore from the top and as it falls down the blast furnace. Iron 3 oxide will react with carbon monoxide to produce iron and carbon dioxide. The iron produced at the top is solid because it's not hot enough to melt, but when it gets to the bottom, it definitely will melt. So we can consider the overall equation to be the one that produces liquid iron. The ore and the iron will travel down the column as stuff is extracted from the bottom. As we get closer to the bottom, we'll have more iron and less iron ore. We'll also have the calcium carbonate from the limestone travelling downwards, but I'll free up some space so we can talk about it properly. At about 800 degrees, the calcium carbonate introduced by the limestone decomposes fast enough to produce the calcium oxide we need. The decomposition of calcium carbonate into calcium oxide and carbon dioxide is endothermic, so this process absorbs some of the heat generated by burning the coke. The extra carbon dioxide produced can also react with carbon to produce more carbon monoxide. In the next step, calcium oxide reacts with silicon dioxide impurities in the ore. This helps keep the silicon impurity levels of the iron at the end low. The calcium silicate produced melts at about the same temperature as iron, so at the bottom it turns molten. At the bottom we have a layer of molten iron covered by a layer of molten impurities like calcium silicate. We call this top layer the slag. The slag is drained away separately to the molten iron, and the molten iron produced in this process is called pig iron. The pig iron produced by a blast furnace is still relatively impure, with about 4% weight by carbon as well as other impurities. This high level of carbon makes the iron, when it solidifies, quite strong but quite brittle. In order to produce steel for structural applications, some of this carbon needs to be removed. This can be done using the basic oxygen process. However, this isn't the focus of this video. Instead, let's do some practice. Which of the following substances found inside a working blast furnace reduces iron ore? A. CO, B. CO2, C, CaCO3, D, H2O, or E, O2. A blast furnace uses a mixture of hot air and carbon in the form of coke to reduce metal ores, like iron ores and lead ores. In the case of iron, the most commonly used iron ore is hematite, a form of iron 3 oxide. Reduction of this iron ore involves removing the oxygen, leaving the iron behind. One way of approaching this question is to consider which of these 5 chemicals is capable of extracting oxygen from iron ore. For this question, I'm going to consider reduction to be the process of removing oxygen from something. We could consider electrons, but thinking about removing oxygen is more straightforward in this case. As a quick test, we can see how these substances respond to molecular oxygen. Carbon monoxide reacts with oxygen to form carbon dioxide, so carbon monoxide is capable of acquiring more oxygen. Therefore, we can consider carbon monoxide a possibly effective reducing agent. On the other hand, carbon dioxide does not react further with oxygen, so it's unlikely to be an effective reducing agent. And this is true of the other 3 chemicals. Calcium carbonate, water, and oxygen do not readily react with more oxygen. This process leaves us with the answer of carbon monoxide, but let's look at this another way. Let's have a look at the role of each of these chemicals in the blast furnace. In the blast furnace, the very role of carbon monoxide is to reduce the iron ore, while the role of carbon dioxide is to react with carbon to make the carbon monoxide. So carbon dioxide is involved in the chain that produces the agent that reduces the ore, but carbon dioxide doesn't reduce the ore itself. Calcium carbonate, usually in the form of limestone, is added to blast furnaces so that it decomposes, producing calcium oxide. Calcium oxide is there to remove silicon dioxide impurities present in the ore. In comparison to the other chemicals, you're unlikely to find H2O in the blast furnace. However, there may be hydrocarbons in the coke, which, when burned, will produce H2O. However, water will not be involved in the reduction of the ore. Let's have a look at the last option. Oxygen is an infamous oxidant, and therefore unlikely to be a reducing agent. In the blast furnace, its role is to react with carbon to make carbon dioxide. Therefore, our final answer for which substance found inside a working blast furnace reduces iron ore is carbon monoxide, CO. And here we have the balanced chemical equation for the reduction of hematite, iron 3 oxide. Finally, let's have a look at the key points. Iron is extracted from iron ore using a blast furnace. Coke, iron ore and limestone are mixed and added to the furnace. The coke reacts with hot air, producing carbon dioxide, which goes on to react with more coke to produce carbon monoxide. The iron ore is reduced by the carbon monoxide, forming iron, which melts at the bottom of the hot furnace. And the limestone decomposes to form calcium oxide and carbon dioxide. The calcium oxide reacts with silicon dioxide impurities, and the molten slag is then drained off. This leaves a molten iron layer that is our product. In operation, the temperature at the bottom of a blast furnace is over 1500 degrees Celsius. We have a layer of molten iron with a layer of molten impurities that we call the slag. At the top of the furnace, the temperature is closer to 400 degrees Celsius. And in between, we have a region at around 800 degrees Celsius where the calcium carbonate begins to decompose.